Regenerative agriculture, or RA, it's gaining serious traction these days, wouldn't you say?
Oh, absolutely. It's everywhere,
And while a lot of the talk focuses on soil health and storing carbon,
which are important,
for
definitely.
sure. But today, we're going to zero in on something absolutely crucial: water.
That's right. And our guide for this exploration is an article exploring the critical role of water in regenerative agriculture, building promises and avoiding pitfalls.
It gives a really, well, deep look at this relationship.
Exactly. So our goal today, it isn't just to echo the common things you hear about RA and water. We want to really clarify how they work together,
Hmm.
looking at the genuine benefits, the promises, as the article calls them,
Right.
but also those potential challenges, the pitfalls that maybe don't get enough airtime. We're aiming to give you, the listener, a much clearer picture.
And to start, the article really emphasizes two key soil properties. These are essential to understanding how regenerative agriculture and water interact.
They are readily available moisture, which they call RAM,
RAM, got it.
and the soil infiltration rate, or SIR. Keep these two concepts in mind as we delve deeper.
Okay, RAM and SIR. Let's unpack this. The article lays out some really interesting promises connected to RA and water. The first one revolves around making sure rain-fed crops get the water they actually need for optimal growth, that evapotranspiration thing we often hear about.
Yeah, and what's fascinating here is how the soil's ability to hold water acts as the key. It's the mediator.
How so?
Well, think about a crop like wheat. It needs roughly 500 to 600 millimeters of water through its growing season.
Okay, quite a bit.
And for sugarcane, that jumps way up maybe 1,000 to 2,000 millimeters. That's a significant volume of water per hectare,
Where's it going?
water the plants need to pull from the soil to really thrive.
Right.
And how readily available that moisture is in the soil, well, that directly dictates whether the need can be met, especially when rainfall isn't consistent.
Right. Makes sense. Okay, the second promise is about managing water's more destructive side, reducing surface runoff and flooding. It's about more than just keeping water on the field, isn't it?
Absolutely. Yeah, if we connect this to the bigger picture,
Hmm.
reducing that rapid runoff, it has a whole chain of positive effects.
Like what?
Well, less soil erosion on the farm, obviously, helps keep that fertile topsoil. But then, at a wider catchment level,
The whole river basin.
exactly, it allows more water to actually soak into the ground. That helps replenish groundwater supplies. It sustains the base flow of rivers, those consistent flows that are vital for ecosystems and other water users downstream.
Mm-hmm.
And it can even improve water quality because the soil acts like a natural filter. Compare that to degraded soils where heavy rain just washes away topsoil, sends sediment downstream, pollutes the water. It's a big contrast.
Okay. The third promise zooms in on managing water more effectively right at the farm level, considering both rainfall and irrigation. The idea is that healthier soil acts like a more efficient sponge, right?
Precisely. Better soil health with improved structure means the soil can capture and hold on to more rainfall when it comes.
Makes sense.
And the article gives a pretty clear example. Let's say a crop needs 700 millimeters of water total. If 200 millimeters come from rainfall that the soil captures,
You need 500 from irrigation.
right. Now, if regenerative practices help that same soil capture an extra 50 millimeters of rainfall,
Then the irrigation need drops to 450.
exactly. That's a direct decrease in reliance on either pumped water or water diverted from rivers,
Yeah.
which is critical, especially in areas facing water scarcity.
And that leads us nicely into the fourth promise, which looks at water management on a much bigger scale. Entire river basins, how water is allocated.
This is where it gets really interesting, I think, when you consider the sheer scale of water used in agriculture globally.
It truly is. Over 70%, 70, of all the fresh water we take globally from rivers, lakes, groundwater, it goes to irrigating crops.
70%.
And in
Yeah.
some drier regions, that figure can climb as high as 95%. 95.
Unbelievable. We're talking hundreds of millions of hectares under irrigation. Massive daily water withdrawals. And the projections for the future are, well, quite concerning.
How so?
Agricultural water use could jump by 70 to 90% by 2050 just to meet projected food demands.
Whoa.
Yeah, it's a stark figure. And it really underscores why any claims about saving water in agriculture, even through RA, need really rigorous scrutiny.
That's a staggering potential increase. And then you factor in climate change. More unpredictable rainfall, maybe higher evaporation. The pressure just ramps up.
Exactly. And while rain-fed agriculture still produces most of the world's food, it's also more vulnerable to these climate shifts.
Makes sense.
The article mentions Falkenmark and Rockstrom, who really emphasize the importance of, and I'm quoting loosely here, capturing more local rainwater on current farmers' fields. The idea is to ease the burden on the overall water resources.
So if RA practices can genuinely boost how much local rain gets absorbed and stored?
But they could be a significant tool, yeah, especially in managing those really tight water allocations in water-stressed areas.
Okay. There's also a fifth promise mentioned sort of indirectly about increasing soil organic matter and locking away carbon.
Right, the carbon sequestration link.
We'll come back to how that connects with those soil water properties Ram and Sur later. But first, let's really get our heads around what readily available moisture and soil infiltration rate actually are.
Good idea. Let's start with readily available soil moisture, RAM. Picture two different soils. One is pretty degraded, maybe compacted. The other is healthier, maybe what we'd call regenerated.
Okay.
Both soils have an upper limit to how much water they can hold against gravity. That's called field capacity, FC.
It's capacity, right?
And both have a lower limit where plants just can't pull any more water out. That's the permanent wilting point, or PWP.
Okay, FC and PWP. So RAM is the water held between those 2 points.
Not quite. The water between FC and PWP is the total available moisture, TAM.
Ah, okay. TAM.
RAM is the portion of that TAM that plants can access really easily without stress. It's the readily available part.
The sweet spot.
Exactly. Think of it this way. A sandy soil, or maybe a shallow soil, might have a low TAM overall, let's say 40 millimeters.
Okay.
Now, if a crop is using, say, 5 millimeters of water each day through evapotranspiration.
That 40 millimeter runs out in about 8 days.
Right. The plant starts feeling drought stress pretty quickly.
Whereas a clay-rich soil, maybe with deep plant roots, could have a much higher TAM.
Yeah, maybe 200 millimeters, for example, with that same 5 millimeter daily use.
It could keep the crop going for 40 days.
Around that, yeah. That's a huge difference in how resilient it is to dry spells, isn't it?
Massive difference. Okay, so TAM is the total potential, but RAM is the easily accessible part within that.
Precisely. Now, RAM specifically relates to the water held in the medium-sized pores in the soil structure. Technically, it's water held between certain tension levels, usually -10 and maybe -100 or -200 kilopascal.
Okay, getting a bit technical, but basically it's how tightly the soil grips the water.
Exactly. RAM is the water held loosely enough for roots to easily slurp it up. And what's really insightful, I think, is that RAM is a strong indicator of the physical health of the soil under RA.
How so?
Well, a soil that's recovering, getting better structure, will tend to hold a higher proportion of its total water, its TAM, in that readily available range. Maybe 40 to 70% of TAM could be RAM.
Which is good for the plants.
Ideal, yeah. And it gives you more flexibility if you're irrigating. A low RAM, say less than 40% of TAM, suggests the soil structure is poor, degraded.
So the key insight is that healthy soil isn't just about holding more water, it's about holding it in a way plants can readily use it.
You've got it. That's a crucial distinction, and one that sometimes gets missed.
Okay, that makes sense. So RAM is about how much water is easily available to the plants. What about the soil infiltration rate, sir?
Right, sir. This is all about how quickly water from rain or irrigation can actually soak into the soil surface. And the structure of that very top layer, maybe the top centimeter or 2, maybe 5, that's absolutely critical here.
Why the top bit specifically?
Because that's the bottleneck. Imagine a less healthy soil. Maybe it's compacted from machinery or it forms a hard crust when it dries out. It might have very few of those larger pores, the macropores, that act like tiny tunnels for water to get in quickly.
Okay.
In that case, the base infiltration rate, the steady rate once the soil is wet, might be really low. Less than 5 millimeters per hour, maybe.
That doesn't sound like much, especially if it's raining hard.
Exactly. If the rain is falling faster than, say, 5 millimeters per hour, and the soil can only absorb it at that rate, where does the rest go?
Runs off the surface.
Precisely. Increased surface runoff, taking soil with it. Now, contrast that with a regenerated soil, maybe a clay soil that's developed better structure through RA practices, more aggregation, more of those larger pores.
The infiltration rate would be higher.
Significantly higher, potentially. Maybe it increases to 15 millimeters per hour, or even more in some cases. That means much more water actually enters the soil profile, replenishing moisture, potentially recharging groundwater, instead of just washing away.
Like pouring water onto dry, cracked earth versus onto a loose, crumbly sponge.
That's a great analogy. That's the difference ours captures. And it's particularly important during prolonged rainfall. If that base infiltration rate is low, you can get surface ponding, waterlogging, which is bad for plants and soil life. Low oxygen.
So a good SIR helps get the water into the soil efficiently, reducing waste, reducing erosion.
Absolutely. And the article makes another important distinction here. It distinguishes between the actual levels of soil moisture and infiltration happening right now.
Like, how wet is it today?
Yeah.
Yeah.
Versus those longer-term soil properties like RAM and TAM and the potential SIR. Crops obviously respond to the immediate moisture levels, but those longer-term properties, they indicate the soil's inherent health and how resilient it will be over time.
Got it. So even if you're constantly irrigating to keep the actual moisture level high, if the underlying RAM and TAM properties are poor, the soil isn't truly healthy or resilient in that regenerative sense.
That's a really key point the article makes. Okay, now let's go back to those idealized promises, those benefits, and see how these soil water properties, RAM and SIR, act as interconnected outcomes.
Right, because it's not like these things happen in isolation, are they? They're all linked up.
Not at all. They're deeply interconnected. Soil porosity, the amount and size of the spaces between soil particles, directly influences both infiltration and how much water can be stored, especially in that readily available RAM zone. You need those medium mesopores for RAM and the larger macropores for good infiltration.
And if water can't infiltrate well because SIR is low,
Then you won't build up the soil moisture levels, you won't fill up the TAM and RAM.
and if moisture levels are consistently too low,
Then the soil structure itself can degrade, reducing porosity, further hurting RAM and SIR. It's a feedback loop.
and that then impacts everything else, how well crops grow and those broader catchment benefits we talked about earlier, like cleaner water downstream and less runoff.
Precisely. Furthermore, these physical soil water properties are deeply linked to soil organic matter, SOM, and the activity of all the living organisms in the soil biological activity, or SBA. These are absolutely central to ROA.
Through practices like no-till, cover crops, mulching.
Exactly. Those practices help build organic matter, and crucially, higher, more consistent soil moisture levels create a better habitat, a better environment for those beneficial soil microbes, fungi, earthworms, and plant roots to thrive.
So the water enables the life.
It does. And that increased biological activity then helps build better soil structure aggregation, which improves porosity, improves RAM, improves SIR. It also helps cycle nutrients more effectively. And ultimately, it makes the soil more resilient to stresses like drought.
So it's all feeding back into itself. Water supports the biology improves the structure improves the water dynamics.
In a healthy system, yes, it's a positive feedback loop.
And that resilience to drought seems like a really major benefit.
It is. Remember our earlier example, the soil with low TAM drying out in maybe 8 days versus the one with high TAM lasting for 40 days under the same water use.
Yeah.
That difference is resilience. It's not just about maximizing yield when water is plentiful. It's about having that inherent capacity, that buffer, to withstand those inevitable periods of water scarcity. Regenerative ag aims to build that kind of natural shock absorber.
It really highlights that water isn't just an input you add like fertilizer. It's fundamental to the whole regenerative process. It's both an input and an outcome.
Exactly right.
Yeah.
Water enables regeneration, and regenerated soils handle water differently, influencing the local hydrology.
And the article emphasizes this isn't simple, is it? It's not linear.
Not at all. It describes a complex system. There are many interconnected factors at play. You've got the natural environmental conditions, soil type, the climate, the local geology, and then you have the human and technical inputs, the specific farming practices, whether irrigation is used and how, all operating at different scales, from the farm plot to the whole catchment, even influencing policy. And there are feedback loops all over the place. It's definitely not a straight line.
So managing RA from a water perspective is really about trying to nudge those key properties, RAM and SIR, in the right direction and sustain them over time.
That's a good way to put it. Using inputs like, say, managed tillage or cover crops can help improve them, while other factors, maybe adverse weather or poor management, can push them backwards, lead to degradation.
Okay, so those promising outcomes really hinge on getting these fundamental soil characteristics right. RAM and SIR seem key.
They are definitely central to the article's argument.
Right. Now, having laid out those potential benefits, the article then pivots, doesn't it? It turns to the potential risks and pitfalls of RA when it comes to water. And the first big one they flag is, well, not properly quantifying the actual volumes of water involved.
Yes, this is a really critical point. The idea that you can just add water to regenerate soil gets much more complicated when you look at the numbers.
How so?
Well, there's a significant difference between the amount of extra water a healthier soil can store, filling up that bigger TAMRAM bucket, basically, and the ongoing water you might need to keep a soil moisture for longer periods to actively support that restoration process, especially while plants are alive and transpiring using water.
Okay, so storage versus active use for regeneration.
Exactly. The article illustrates this with three calculations, which are quite eye-opening.
Okay, let's walk through them. Calculation 1 looks at that extra storage potential.
Right. They use an example. Imagine you increase RAM by 50 millimeters across a pretty big area, say 20,000 square kilometers.
That's up
That
to,
sounds like a lot of water stored, and it is about 1,000 million cubic meters, or 1 billion cubic meters.
okay, huge volume.
But the article points out to actually fill that extra 50 millimeters of storage only requires an effective rainfall event, or equivalent irrigation, of 50 millimeters depth. So in terms of the sheer volume needed to fill the extra storage capacity once it's created, RA doesn't necessarily put a huge additional one-off burden on water resources at that large scale.
Interesting. So reaching that healthier state in terms of storage capacity might not need impossible amounts of water, but calculation 2 looks at the ongoing need, keeping soils moist for the regeneration itself.
Exactly. This is where it gets tricky. This calculation compares a degraded soil scenario with a regenerated one. It looks at the extra irrigation you might need to keep the regenerated soil moist for longer each year, say, extending the moist period by an extra 100 days beyond the typical growing season, specifically to encourage that biological activity, the soil building processes.
Okay, so purposefully keeping it wetter for longer.
Yes. And it also factors in slightly higher water use by plants in the moisture soil, more transpiration, and maybe slightly less efficient use of irrigation water during that extended period.
And the result?
The results are quite striking. In their example, it showed a potential increase of over 129% in the total volume of water depleted, that's water used by plants, plus evaporation, just to achieve this extended moist period for regeneration on 10,000 hectares.
Wow, more than double the water use for that area.
In that specific scenario, yes. It highlights that while RA might improve the soil's capacity to hold water, the active process of regeneration, especially if it involves maintaining higher moisture levels for longer durations, could dramatically increase overall water consumption or depletion from the local system.
That's a really significant potential jump. And the third calculation puts that into the context of a water-scarce region.
It does. It takes that extra irrigation demand calculated in the second step and applies it to a hypothetical guesstimate that already has limited renewable water resources and existing essential water needs, like for towns or critical ecosystems.
And what happens?
Even with that extra demand coming from a relatively small area, just 10,000 hectares wanting regeneration water, it could be enough to flip the catchment's water balance. It could shift it from having a small surplus of water to being in a significant deficit.
And that's just for 10,000 hectares. Imagine scaling that up.
Exactly. So the question arises, does this potentially massive increase in water demand for active regeneration mean we should be perhaps more cautious about pushing RA, especially heavily irrigated RA, in already water-scarce regions, even if the long-term soil benefits are there? It's a trade-off.
It really underscores that we can't just assume regenerating soils automatically means using less water overall. That extra water potentially needed for the regeneration process itself is a critical factor that often seems to get glossed over.
Precisely. The article explicitly asks if water might be a weak link in the whole push for soil carbon sequestration through restoration, given these potentially large unaccounted-for water demands.
A weak link. That's provocative.
And it stresses that if we are using irrigation water for regeneration, it needs incredibly careful management. We need to ensure it actually functions regeneratively within the soil profile and isn't just lost to evaporation or deep drainage, potentially causing other problems.
Okay. Pitfall number 2. Not all soil water is the same. This relates back to RAM, doesn't it? It's not just about the total amount.
That's right. It goes back to that distinction between total available water, TAM,
Yeah.
and readily available water,
Yeah.
RAM. Let's use their example again. A soil with a TAM of 120 millimeters, and let's say the RAM portion is the first 60 millimeters, from PWP up to a certain point.
Okay.
Adding the same volume of water, say 30 millimeters, has a very different effect depending on where you add it. Adding 30 millimeters when the soil is dry, going from 0 up to 30 millimeters, still well within the tightly held water zone below RAM.
Plants might still struggle to get it.
Potentially, yes. Or it mainly benefits just basic survival. Now, add that same 30 millimeter when the soil is already at, say, 40 millimeters, taking it up to 70 millimeters, pushing it well into and maybe slightly above the RAM zone.
That's much more beneficial for growth and soil life.
Exactly. It has a very different impact on plant transpiration and soil biological activity.
Hmm.
So just knowing the total moisture content isn't enough. You need to know where it sits relative to that RAM threshold.
So simply hitting a target moisture level doesn't guarantee the water is in the most useful form.
Correct. Water held below that RAM threshold is much harder for plants to extract. And maintaining moisture levels consistently above that threshold, which is often desirable for optimal crop production and for promoting soil regeneration well, that's likely going to require irrigation in many rain-fed farming systems, especially during dry periods.
Mm.
The article also adds a nuance about organic matter here. While SOM generally improves the total water holding capacity, TAM,
Yeah, we hear that a lot. More OM, more water storage.
and it's true, but its biggest benefit, especially in coarser soils like sands, might actually be in improving the pore size distribution, creating more of those medium-sized pores that hold water in the readily available RAM range. So it's not just holding more water, but holding more of it usefully.
Okay, a subtle but important distinction. Pitfall number 3 seems really fundamental. Not clearly separating regenerative ag and rain-fed areas versus irrigated areas. They're really different beasts when it comes to water management.
Oh, completely different. In rain-fed systems, your main lever for managing soil moisture is indirect. It's improving the soil's ability to capture, store, and efficiently use whatever rain falls. Practices like cover cropping, mulching, no-till.
You're working with the rain you get.
Exactly. In irrigated systems, you have direct control. You decide when, where, and how much water to apply through irrigation scheduling. But as the article points out, managing irrigation effectively to be efficient for the crop, to support soil regeneration, and to fit within water allocations is incredibly complex.
It's not just turning on the tap.
Far from it. It involves technical know-how, but also huge social, political, and economic factors. Water rights, infrastructure costs, energy use, farmer cooperation. It's a whole different ballgame. And things like the specific type of clay in the soil, which we touched on, will massively influence both RAM and SIR locally, making generic irrigation advice pretty useless.
They use that example of 25 farmers facing a drought, comparing rain-fed and irrigated situations. It really drives the point home.
It does. The rain-fed farmers have very limited options, basically hoping their soil improvements help them ride it out. The irrigated farmers, even if water is rationed, still have choices. They could adjust timing, amounts, maybe prioritize certain fields. Their capacity to adapt is just fundamentally different.
And what about things like drip irrigation? Isn't that often touted as a solution? Precision irrigation?
It is, and it can be very efficient at the field level. But the article raises several cautions. High upfront costs can be a barrier, especially for smallholders. It often requires more energy for pumping, which has carbon footprint implications. It's not suitable for all crops or soil types.
And the big one.
The big one is the potential for what's called the paradox of efficiency. If irrigation becomes more efficient at the farm scale, it can sometimes lead to more land being brought under irrigation or growing thirstier crops, potentially increasing the total water consumption across the entire basin.
So field savings don't always equal basin savings.
Exactly. So precision irrigation needs careful planning, supporting infrastructure, and strong regulations to avoid those unintended consequences.
And the idea of just adding a little bit of extra or supplementary irrigation to rain-fed systems, is that a simple fix?
The article suggests it's not as simple as it sounds. Given how variable rainfall can be in both time and space, trying to precisely manage small top-ups across a large area that's also getting unpredictable rain is incredibly challenging, both technically and logistically. That applies whether you're just trying to meet basic crop needs or aiming for that extended soil moisture period for regeneration.
Plus, irrigation itself isn't always benign for soil health, is it?
No, definitely not. If managed poorly, it can lead to problems like leaching valuable nutrients, soil salinization, salt buildup, waterlogging, killing roots and beneficial microbes, soil compaction, and just generally encouraging more intensive farming that might degrade soil over time.
So, achieving truly regenerative irrigation on a large scale.
It would require, as the article puts it, an extraordinary adaptation and regulation of existing irrigation systems. You'd need to fundamentally shift the focus towards managing soil moisture dynamics, specifically RAM, within the very real constraints of water availability. That's a huge ask.
Okay. Pitfall number 4 is a bit sobering. The potential for setbacks. Reversals caused by environmental disturbances. It's not always a smooth upward curve of improvement.
Exactly. Real-world ecosystems, including agricultural ones, are not linear. They're dynamic. They're subject to shocks and stresses that can undo progress made in building soil health and organic matter.
What kind of stresses?
They can be short-lived, intense events, things like severe droughts, wildfires, extreme heat waves, major erosion from freak storms. These can rapidly deplete soil moisture and oxidize, burn off organic matter.
And longer term stresses.
Those can stem from the farming practices themselves if not managed well. Think gradual salinization from irrigation, over-irrigation leading to waterlogging, soil structure damage from erosive tillage practices, or negative impacts from agrochemical residues. Even with the best intentions, things can go backwards due to factors sometimes outside the farmer's control.
Right. A dose of realism. Pitfall 5 brings us back to carbon sequestration, questioning if we fully grasp water's role in that whole process.
Yeah, this is a deep one. The article raises a crucial point. Does current research adequately explain the complex interactions? How exactly does water, interacting with soil texture, wetting and drying cycles, soil pH, salinity, the existing organic carbon, and all the soil biology, how does all that actually lead to the formation of stable, inert, organic matter, IOM, the stuff that sticks around for a long time? Especially when you consider that microbes are constantly respiring, releasing CO2 back into the atmosphere.
So it's not a given that making the soil moisture automatically locks up more carbon long term.
It's uncertain. Optimizing soil moisture, whether through better rainfall capture or irrigation, clearly helps grow more biomass, more plants, more roots, more microbial activity. But that increased moisture and activity can also increase the rate of respiration, the breakdown of organic matter. So the net effect on long-term stable carbon storage isn't always clear-cut. It might depend heavily on the specific soil, climate, and management.
And there's a concern about the technologies sometimes proposed for boosting carbon storage, like subsurface irrigation or intensive water harvesting.
The concern is that these aren't always fully costed, you might say, not just in dollars, but in terms of their water footprint, their social implications, their economic feasibility across different scales and regions.
Are they practical everywhere?
Probably not. Many might be too expensive or technically complex for smallholders or in developing regions. And even where they are implemented, the fact that we're usually still harvesting biomass, crops, residues, from the system means the net gain in long-term soil carbon might be limited. It's an area with lots of questions still.
Okay. The next pitfall tackles some buzzwords we hear. Net zero water, or net positive water, in the context of RA. The article suggests these terms might be misapplied here.
Yeah, this is quite insightful. It draws a distinction between closed or semi-closed systems, like maybe an urban water supply or a manufacturing plant, where you can track inputs and outputs relatively easily and potentially recycle or offset use.
Right.
And the wide-open hydrological cycles that agriculture operates within, a farm, a catchment, a whole river basin, these are open systems. Water flows in, rain, irrigation flows out, evaporation, transpiration, runoff, deep seepage, in complex ways that are hard to perfectly measure or balance.
So applying terms like net positive from other sectors doesn't really fit.
The article argues it's problematic. Claims that RA can be net positive for water at a large basin scale are largely untested and probably unrealistic. You can't just assume that water used by crops or evaporated from soil in one place is somehow automatically replenished or offset somewhere else in that basin in a way that negates the fact that it was used, that it's gone from that part of the cycle. There's an opportunity cost to that water use.
So it's not like carbon offsets where you can sequester carbon here to balance emissions there. Water doesn't quite work like that in an open basin.
That seems to be the argument. They suggest it's more helpful to focus on the water balance at a more local level, understanding the ins, rain, irrigation, and the outs, evaporation, transpiration, seepage, runoff, within that specific farm or field context.
And viewing regenerated soil not as creating water, but maybe as a better gatekeeper.
That's a good way to think about it.
Yeah.
A regenerated soil acts like a better gate. It slows water's passage through the local system, maybe improving infiltration, more going in, directing more towards beneficial plant transpiration rather than unproductive evaporation or runoff. But it's not creating net water or saving it in a way that means it's available elsewhere in the basin. It's changing the local partitioning of water.
Okay. The seventh pitfall asks the million-dollar question directly. Does RA use less water? Seems simple, but the answer isn't.
Not simple at all. It's highly context dependent. There are arguments on both sides, as the article lays out.
Argument for less.
Healthier soils with better structure, better RAM and SIR, can capture and store rainfall much more effectively. This could mean less need for supplemental irrigation and rain-fed systems, or more efficient use of irrigation water when it is applied. So potentially less water needed from external sources.
Okay, argument for more.
Well, degraded soils might actually need more frequent, less efficient irrigation just to keep crops alive. And counterintuitively, perhaps, a really healthy, well-watered, regenerated soil supporting vigorous plant growth might actually transpire more water overall than a struggling crop on poor soil. More biomass often means more water use.
And then there's that paradox of efficiency again.
Exactly. Water savings achieved through better soil health or more efficient irrigation at the individual farm level might, paradoxically, lead to increased water consumption across the whole river basin if it enables expansion of irrigated areas or shifts to thirstier crops.
So the answer to does RA use less water is it depends.
Pretty much. It depends hugely on the scale you're looking at. Field versus farm versus basin. The starting point, degraded versus reasonable soil. The context, rain-fed versus irrigated. And crucially, requires really accurate water accounting at the relevant scales to understand the net impact. It's not a simple yes or no.
Which leads perfectly into the final pitfall, the risk of applying blueprint solutions and ignoring local conditions and, crucially, local voices.
Yes, this is paramount. The article stresses that context is everything. What works in one place might be totally inappropriate or ineffective somewhere else. Site-specific dynamics, the soil type, the microclimate, the slope, the existing vegetation are critical.
And just as critical are the farmers themselves, right? Their specific situation.
Absolutely. Their knowledge, their resources, their land tenure security, the market access they have, the policies they operate under. All these factors shape what's possible and practical. You can't compare the situation of a farmer in, say, a humid, well-subsidized region in Europe or North America with a farmer in a semi-arid, marginalized area in Africa or Asia facing insecure land rights and limited access to inputs or credit.
Their capacity to adopt RA practices, especially those requiring significant investment or changes in water management, will be vastly different.
Completely different. So top-down, one-size-fits-all approaches are almost guaranteed to fail. Listening to and working with farmers within their specific contexts is essential.
Okay, so we've taken a real deep dive today into this complex, interconnected world of regenerative agriculture and water. We've looked at the exciting promises, but also flagged some pretty significant potential pitfalls. What are the main takeaways for you, summing up?
Well, first and foremost, it's undeniably clear that water plays this fundamental, really multifaceted role in RA. It's deeply tied to those key soil properties we discussed, readily available moisture, RAM, and soil infiltration rates, sir.
Right. The promises are real, but realizing them isn't automatic.
Exactly. Achieving the potential benefits, better water use, healthier soils, improved resilience, and avoiding those pitfalls requires a genuinely nuanced understanding. We have to appreciate water's multiple roles and the sheer complexity of hydrological systems, especially when agriculture is involved.
And it really hammered home that water in RA is both an input and an outcome. It drives the process, but the process changes how water behaves.
Yes, and it all operates within these complex, often nonlinear systems where actions can have unintended consequences somewhere else or down the line.
So we really need to move beyond maybe some of the simpler, overly optimistic narratives.
I think so. The key seems to be focusing on quantification, actually measuring the water involved, conducting analysis that is specific to the local context, and always clearly distinguishing between rain-fed and irrigated agriculture. They are just fundamentally different.
And we definitely need to be careful about evaluating the real water requirements for soil regeneration itself, especially where water is scarce, and perhaps be skeptical of easy claims about net zero or net positive water use in this context.
Agreed. Those terms need very careful application, if at all, in open agricultural systems.
And ultimately, it comes back to the ground level, doesn't it? The success hinges on understanding local conditions, respecting site-specific dynamics, and genuinely valuing the perspectives and knowledge of the farmers working within those contexts.
Precisely.
Yeah.
Which I suppose leads us to a final thought, a question really, for you, the listener, to mull over. Considering the immense and growing water demands of both feeding the world and potentially restoring our vital agricultural soils, and layering on top of that the increasing pressures on water resources globally from climate change and other uses, how do we best prioritize and manage water in this necessary transition towards more sustainable agricultural systems like RA?
Mm.
What difficult trade-offs might we actually need to confront at the local farm level, at the regional basin level, and even globally? It's not an easy question.
No, it certainly isn't. Really powerful questions to think about. We definitely encourage you to explore the source material we've discussed today in more detail. The article raises many more points, and Table 4, in particular, poses some key questions for analyzing water in RA that are worth considering. Thanks for